I've never used it for science.
All right, let's
Clearly they do.
let's rumble. Okay, so thanks everyone for being here. I think half the atmospheric scientists are probably still staring out the window as they do in this building. Anytime there's a storm, it's a thing. It's really a problem. No, I love them. Some of you are in here still, so thank you for that. So it's my great pleasure to introduce Andy Thompson. He is a professor at the California Institute of Technology of Environmental Science and Engineering. He's a professor of that. He's been there since 2011. Prior to that, he got his PhD from Scripps Institution of Oceanography and spent quite some time in the UK doing all sorts of interesting things, including working for the British Antarctic Survey. You've done some field work in the past, and hopefully will continue to do field work because I like just learning about it. So Andy is interested in a lot of different things, from circulation of the Southern Ocean and the Antarctic margins, all the way to mesoscale and submesoscale ocean dynamics, as well as turbulence and variability generated by ocean-ice interactions. He's won some pretty nifty awards that I like to talk about here, because there's a giant list. This is the thing. It's okay, I'll make you feel uncomfortable now. Including the AGU Ocean Sciences Early Career Award, and he also got a Packard Fellowship for Science and Engineering back in 2014. So he has done some really awesome work, and he's been an inspiration to me a lot as I've kind of grown in my own career. And so it's really exciting to have him here today to talk to us about transitions in the global overturning circulation. So thank you.
Awesome, man. That was a fabulous introduction. I really appreciate it. Thanks everyone for coming out. This is my first trip to Madison, and it's been really fun today. I've really enjoyed the conversations I've had with everyone. So thanks very much for your time. Okay, so I'm going to talk about transitions in the global overturning circulation. I kind of chose this because Channing Friend, maybe some of you saw Channing's talk a couple weeks ago, and he talked about Southern Ocean stuff, and I thought I should do something different. Conversations I've had, this has been great because it sounds like a number of people are working on these topics. So I would love to have feedback as the talk's going on. Feel free to stop me, ask questions along the way. Okay. And of course, this is work that what I'm presenting is largely led by a number of very talented students and postdocs on here, plus one colleague who you might know in the lower right. And I just want to acknowledge all their hard work. The work that I'll show today is mostly based on work that Emily Newsom, Shantong Sun, and Dave Bonin. So Emily and Shantong have gone off to bigger and better things, but Dave's still a graduate student at Caltech. But really all of these people have helped me think about what I'm going to talk about today. Okay, so I'm going to spend the first 10 minutes doing a bit of a background, because I appreciate there's probably a broad audience here. And the two things I'm going to talk about a lot today are the ocean's density structure, and then I'm going to talk about the overturning circulation. So I want to introduce what these are and what they look like. So the very first thing you always need to show in an oceanographic seminar here is take a slice through the ocean. Okay, so what you're looking at here, this is a section through the Pacific Ocean, so depth on the y-axis, latitude or meridional distance on the y-axis here. And if you were to cut through the center of the Pacific Ocean and open it up, this is what it would look like. Okay, and there's three features here that I want you to see. Two we're going to focus on. First, notice that there's sort of this, all of these contours here are contours of constant density. So the ocean is stratified. You can see these bowl-shaped structures, which are a signature of the ocean's subtropical gyres. But I mostly want to focus on what's happening in the interior. And if you look at throughout most of the ocean, so from about 35 south all the way up to the northern hemisphere, those density surfaces are largely flat. Okay, that's important. And then the one place where you get a deviation away from those flat density surfaces is in the Southern Ocean, where these tilt quite dramatically, at least with this aspect ratio, right, up towards the surface. That allows you to bring deep waters up towards the ocean surface. And what we want to think about today is sort of the large-scale pole-to-pole circulation that affects tracers through the deep ocean, or what we call the overturning circulation. And we're going to think about how it sits on top of this density space. Yep.
You invited questions, Andy. I'm going to ask you one right away. Why did the tilted density surfaces allow upwelling? I can understand there'd be a jet there, right? There'll be a thermal wind maximum in that region of density. So why does that? Is there a circulation associated with the jet that drags fluid up?
So we're going to talk today, and this is like my next slide, about the importance of moving water from one density class to another. And what this does is this region of the ocean allows you a pathway for waters to move up from 2,500 meters to the surface along that same density surface. So you don't actually have to modify your water to move along that pathway.
Okay, but does some circulation compel that, or is it just
Yep.
free?
It is largely due to a sort of a surface divergence that draws water up.
Okay,
yep.
thanks.
No worries. Okay, so part of the reason for showing that realistic picture is I'm going to now sort of idealize the stratification of this picture. This is still depth, this is latitude. I'm going to treat a few density surfaces as being flat in the low latitudes and then tilting here in the Southern Ocean. And what we talk about when we think about the overturning circulation is a velocity structure, right, that carries waters from one latitude to another and may have some distribution that looks like this. When we talk about the overturning circulation, we typically talk about it in terms of a stream function. And that would be taking this velocity field and integrating from the surface to depth, accumulating the transport, and when you do that, you would get a stream function that gives you what we call an overturning cell. Right? So we call it the overturning because it goes around in this way. This is how we typically talk about the stream function. I want you to basically forget this already, okay? And I want to argue that a much better way to think about what the overturning circulation is, it is a circulation that arises, okay, to connect regions of buoyancy gain to buoyancy loss. Or alternatively, there is only an overturning circulation if you can take a water mass, okay, and it changes its density somewhere in the ocean, so maybe it becomes dense and sinks in the north. It then may move to a very, very different region of the ocean, may upwell along these density surfaces, where it can be converted back to that same density class and then can become closed. Okay, and again, I think the difference here is what this means is you can think of the ocean as a series of density layers, and what sets its steady state configuration is a balance between processes that are bringing volume into that density class and processes that are removing it. And so the reason why I think that's useful is that if we now move away from the steady state picture and we think about perturbations or changes in the overturning circulation, one can imagine now that I'm removing one of the processes, say, that brings water into this density class. Changes in the overturning circulation have to be directly connected to changes in the stratification. And that's kind of what I'm gonna push today, not just thinking about the velocity field. Okay, I'm going to start using terms like density and buoyancy interchangeably, so just a few definitions up front. When I talk about buoyancy in the ocean, these are perturbations away from some background mean density of the ocean, and those perturbations arise from either heating or freshwater anomalies, so they can have a thermal and a freshwater content. Okay, so the last thing I want to do, just sort of in my introduction, is do just a couple minute, incredibly truncated view of what our thinking has been of the overturning circulation over time. So if we go back to 1950s, 1960s, there's a seminal paper here by Walter Munk, 1966, called Abyssal Recipes. The picture of the global overturning circulation as waters being sourced to the deep ocean through becoming dense and sinking was localized to very specific places, largely around the poles and in particular in the North Atlantic. And if we think about that water sinking to a deep density class, remember we said we close the overturning by being able to return it to those original lighter density classes. That process was thought to be much more broadly distributed throughout the ocean. In fact, it was basically thought to be uniform. And if we think about where that buoyancy comes from, it comes from heating at the surface. And so if I have to take water that's sunk to the seafloor and make it lighter to bring it up across the density surfaces, the focus was not so much on how much heating was coming to the surface, but how efficiently the ocean could mix it down into the interior. Okay, and that was really the driver of what set the overturning circulation. And in the 60s, when Walter started this, we didn't have any observations, so he said it's uniform throughout the ocean. And that sort of picture held for about 30 years until we finally could actually make measurements of the mixing rate. Okay, and so the first was actually just put some tracer out in the ocean, watch how it diffuses over time. The number that they got was a factor of 10 too small from what Walter Munk had predicted, and everybody went, oh no. And then a few years later, we could actually make direct measurements, and this picture came about. You're looking at a section now. Brazil would be over here, and this is extending eastward into the Atlantic Ocean. This is depth, this is longitude. And what you're looking at in color here is the efficiency or the mixing rate at which the ocean is mixing that heat or buoyancy from the surface down into the interior. And there's a nifty color scale here, which is normalized by Walter Monk's prediction in 1966. So any place where it's blue or purple, it's about a factor of 10 smaller than what he predicted. But any place where it's orange or red, it's larger. And in these red places by an order of magnitude or more. And so the first suggestion was, maybe it's just that when we measured with the tracer, it's because the mixing rates are very heterogeneous. Okay, and that Perhaps if we go everywhere in the ocean and measure this, we integrate, we get a very different picture. But there was one other way out of this conundrum, and that was we also realized, it would have been the late or mid-90s, right, that there were certain density classes that actually outcropped or hit the surface in both the northern hemisphere and the southern hemisphere. And this pointed out an important role for the Southern Ocean, which I've sort of wanted to introduce right from the start, the fact that you have these very strong tilting isopignals in the south that would allow you to bring water from the deep ocean up to the surface without having to mix that buoyancy down into the interior. And we talked about these as adiabatic pathways. And once we appreciated the importance of the Southern Ocean, we sort of had this two-cell picture that I'm going to come back to later in the talk, so I'm not going to talk about it too much now. But it suggested that there's an upper cell and a lower cell. And so the last thing I want to introduce here is that this picture of a two-cell overturning is largely a construct of taking a zonal or an east-west average. Okay? And the last, I think, addition that we've had from a number of papers over the last years, in particular Lynn Talley's nice paper in 2013, suggests that actually the ocean has this three-dimensional single loop, where if I were to follow a water mass here, you have sinking in the Atlantic Ocean, it moves through the Atlantic, comes up through the Southern Ocean, but then sinks a second time, and say may go into the Pacific, and then ultimately upwells and comes back. And you have this important role for exchange between the basins. And I'm going to come back to that exchange in a minute. Okay, so this is, I think, where we are in terms of thinking about our overturning, our understanding of the overturning. And I just want to point out, I think, two things that the theories of the global overturning have really ignored. First of all, as I tried to point out, it's really been focused on the mixing in the ocean, right? How has buoyancy been mixed from the surface into the interior? And very little attention has been paid to thinking about what is just the magnitude of the surface buoyancy force in the heating, especially at the low latitudes. And that's sort of the first thing I'll address. And then the second is thinking about these physical processes that govern overturning transitions, and I'll sort of be the second part of the talk. Okay. Any questions before I move on at this point? All right, good. All right, I told you I wanted to start at the surface, so let's actually look at a map of what the ocean's surface heat flux actually looks like. Okay, so here's a map. Here's latitude, here's longitude. What you're looking at in color here is the ocean surface heat flux. Any place where this is red, you have heat going from the atmosphere into the ocean, and anywhere where it's blue is you have heat leaving the ocean and going into the atmosphere. A couple features stand out. You have this pattern of ocean heat uptake and loss here happening in the low and mid latitudes. This is a consequence of our sort of subtropical gyres, where you bring warm water up to western boundary currents. You also have very cold and dry winds blowing off the continents here, over Asia and over North America. But if I zoom out and sort of look at what is the region where the ocean is taking up heat, it's largely confined to a small band of latitudes right at the equator. This is actually because this is a place where you have upwelling, you bring cold water up, and so it's a very efficient place for the ocean to take up heat. And then if you also just look at the geometry of the ocean, the Indo-Pacific basin, so the magnitude of the heat uptake, say in the Pacific and the Atlantic, pretty comparable. But the width, or just the size of the Indo-Pacific basin is much, much larger, that most of the ocean heat uptake happens in the Indo-Pacific. If I then move to look at where there is ocean heat loss, there is these regions of heat loss in the western boundary currents. We'll come back to that. But because, again, a geometry issue here, because the Atlantic basin extends much further to the north, you have most of your heat loss here in the Atlantic basin. And so if I just do a budget at the basin scale, so let's say we just draw a line across 30 degrees south, kind of connects the tip of Africa, and I just integrate the total heat input into each basins, the heat budget is not closed, surface heat flux is not closed at the basin scale. And we have net heat uptake in the Indo-Pacific, implying, if the ocean's in a steady state, that you have to have export across 30 south. And we have net heat loss in the Atlantic, implying that you have to have heat transport northward into the Atlantic. And so if you actually go into the ocean, this is indeed what you see. So here's a nice paper that Emily Newsom led a couple of years ago, where she did sort of the standard thing. So this is a numerical model. This is depth. This is latitude. This is the Atlantic basin. This is the Pacific, or the Indo-Pacific basin. And the colors here are showing the magnitude and strength of the overturning. And you have red here is a clockwise overturning circulation that's bringing waters into the Atlantic and back out. And in the Indo-Pacific, you have an overturning circulation of the opposite sign that goes around this way. But what she did is she also mapped on here the contours of buoyancy transport. So these sort of look like a stream function, like a volume transport, except they're doing buoyancy. And the big difference is the volume transport has to go zero at the top and the bottom because you don't have a volume flux out of the surface or across the sea floor. But of course you do have a transfer of buoyancy or heat across the surface. So you can use these contours as sort of looking at maps of where heat comes into and out of the ocean. And so if I look at just the total buoyancy input, this is what I showed you before, most of the buoyancy transport into the ocean happens in the Indo-Pacific. There's a little bit here in the Atlantic, but it's much smaller. Some of this heat or buoyancy comes in and sort of just moves around those gyres and comes in at low latitudes and goes back out in those western boundary currents. But there is a very important component that sinks to a depth of about 1,000 or 2,000 meters and is directly transferred into the Atlantic, right? Which is eventually transported northward and lost at the surface, which is part of what forms our deep water in the North Atlantic. And so what I'd like to argue through the next part of the talk is we can think about this process of how the Indo-Pacific takes up heat in various different climate regimes as a way of structuring the overturning circulation, and in particular, this exchange between the different ocean basins. Okay, so that's a little bit of a hypothesis. So in a warming climate, the overturning adjusts to accommodate increasing heat surplus in the Indo-Pacific, and I'm going to test that in, I should be careful, it should say a warmed climate, so I'm not going to do the transient experiments yet. Yes?
I mean, if you change the relative width of the two basins, presumably if you've inverted, then you reverse the circulation?
Yeah, so well, that's right. So the width is part of it, and then the other thing that I mentioned, right, is if you think of the Atlantic, it looks much more like a shoebox, right? It's relatively large and square, and the Indo-Pacific looks more like a pyramid, right? So the fact that the Bering Strait, there's not much transport through there, I think is also a reason why we don't get much deep water formation in the Pacific. But there's some nice work by Sarah Reagan at University of Washington, who has looked at changing the geometry of these different ocean basins and whether you can change the. Okay, so the tool or the suite of simulations I'm going to talk about first come from a paper that was published by Galbraith and De La Vergne a few years ago now, which were these long-time integrations. It's a couple climate systems, so it has an ocean, atmosphere, and biogeochemical component. They're fairly coarse, but they use a number of different ice sheet configurations and different orbital forcings. The forcing for these different simulations are different concentrations of atmospheric CO2. So these are different climate states. And what's really important for these simulations is that the integration time for all of them is many thousand years. So we're going to treat them as quasi-steady different climate scenarios. What I'm showing on here is just the range of all the simulations. You don't have to worry so much about the symbols because I'm only going to look at sort of the variations as a function of CO2. So these were the range of different atmospheric CO2 values that were used, everything from sort of glacial-like climates to pre-industrial, sort of modern day, and then quite warm climates. And you can see for the most part that we can think about atmospheric CO2 and global mean surface air temperature almost interchangeably, right? So as atmospheric CO2 goes up, global mean surface temperature goes up. Okay, so what did we learn from these simulations? Here are the first two important things. So I'm taking all of the simulations, not worrying about the sort of orbital forcing, just averaging over those, for the different atmospheric CO2 values, and then plotting them across their global mean temperature. And again, remember, as this goes up, global mean temperature goes up. But what's on the y-axis here is what I'm calling the Indo-Pacific heat surplus, right? So that is the surface heat flux integrated over the Indo-Pacific basin that I showed you before, that there is this net surplus that implies an export out. And what you find is that as global mean surface temperature goes up, the Indo-Pacific heat surplus also increases monotonically. So the warmer the climate, the more heat the Indo-Pacific basins are taking up, and presumably, if it's in a steady state, the more it has to export out of the Indo-Pacific. And what we find is over those same simulations, if we also just look at the total strength of the global overturning, so the sum of an upper and a lower overturning cell, that also increases monotonically. And I think about this as the ocean is taking up more heat, it has to export more heat, and so it has to strengthen the overturning to more efficiently export that heat. So let's actually look at how the ocean does that by looking at the ocean's surface heat flux, thinking about, again, the sort of total heat budget, and we're going to look at it in 3 different states. Okay, so the first is, let's look at the coldest climate. What you see on here, again, is the surface heat flux, like I showed before. These lines are showing where the sea ice extent is in this cold climate. And you get a picture that looks pretty similar. Heat uptake happens in the low latitudes and predominantly happens in the Indo-Pacific. Heat loss now is largely localized to the western boundary currents. And in this coldest climate, what you find is that if you do that integral across 30 south, so you just calculate the total surplus, the heat budget is largely closed in the Indo-Pacific alone, right? And there's not a requirement to export much heat from the Indo-Pacific. What I'm going to show now is that same surface heat flux, but now this is an anomaly away from the cold climate. Okay, so you have to wrap your head around this a little bit. If I look just at the Indo-Pacific to start, notice that the change in the low latitudes is pretty small. The amount of heat being taken up is about the same, but the western boundary current has become red, which means actually it's become a less efficient place to lose heat. And that's pretty interesting. That is largely because the ocean temperatures that are coming up are not changing very much because they're coming from the equator regions, but the atmospheric temperatures are changing a lot. So your temperature difference between the atmosphere and the ocean are changing significantly. This gives you a larger heat surplus in the Indo-Pacific, and notice now that in a warmer climate, I've melted back that sea ice and I've opened up a region of very strong heat loss in the North Atlantic. And we suggest that this gives rise to a stronger interbasin exchange. And I'll show that overturning in a minute. And the last thing I'll show is now the anomaly of the surface heat flux in this warmest climate, or the hot climate, I should say, away from this warm climate. What's interesting here is that we lose the heat loss a little bit in the Atlantic, but there's not a big change in the northern hemisphere. What happens is we open up heat loss in the southern hemisphere. And so if I sort of map that now onto the overturning circulation, what I've done now is, remember, the total overturning increased monotonically, but I'm separating this now into the upper cell, or the AMOC, and the lower abyssal cell. And so what you find is global mean temperature increases. There is this increase in the strength of the overturning, but it's dominated by the AMOC. Right? So as you first warm the climate, the first mode of exporting that heat from the Indo-Pacific is into the Atlantic. You strengthen this sort of inter-basin mode, and you strengthen the AMOC until the sea ice goes away. And then the AMOC essentially saturates. It no longer becomes an efficient place to lose heat. And when that happens in those warmest climates, what happens is you begin to transfer heat across the Southern Ocean, and you begin to spin up your abyssal cell. You begin to do water mass transformation in the south, and you spin up that lower cell. So you get this transition from heat being exported from the Indo-Pacific into the Atlantic, and then ultimately into the Southern Ocean. So why might that be important? Maybe just one slide here about implications. Here's a global map of increases in surface atmospheric temperature between the warm and the cold state. Okay, so that first transition by turning on the AMOC. As we have seen in lots of climate models, what you get is polar amplification. So the global mean temperature change is about 5 degrees. The color bar here is the change in temperature normalized by the mean. Okay, so in the northern hemisphere, you get changes of 15, 20 degrees. And in the low latitudes, it's pretty small. But note that that polar amplification is confined only to the northern hemisphere. And I'd like to argue part of that is due to atmospheric processes, but we'd also like to argue that part of that is due to the fact that we've turned on the AMOC, and we're bringing heat up through the Atlantic to the northern hemisphere. And if I contrast this with what happens when I move from the warm to the hot state, right, I get a similar increase of about 4 degrees global average. But now if I look at where that amplification happens, it happens both in the northern hemisphere and the southern hemisphere. And again, I'd like to suggest that part of that reason is because now we've moved into a mode where some of that heat from the Indo-Pacific has to be transferred across the Antarctic Circle polar current and into the south. And so this is this work summarized in Emily's paper. There's also a nice paper by Emma Beer, who's a grad student with Ian Eisman at Scripps, who has also sort of run a quite simple model that sort of shows these same dynamics and the importance for heat transport, for ocean heat transport for polar amplification. Yep.
Can you just remind me quickly again what the the cold state is. Is
Yeah.
it colder than our current?
Yeah, so cold was the coldest atmospheric CO2 was about 147,
Okay.
and the warm state was 400.
Okay.
So it goes from 147 to 400 ppm for warm minus cold, and then this goes from hot is 900 ppm.
So a lot of that polar amplification is stuff we already see in our system of the Arctic being warmer than
Yeah, so this
currently.
so in fact, if you want to go a step further and be, I think, a little bit more speculative, right, because we're still very much in a transient state, is that what we see today is that the polar amplification is indeed dominated by the Arctic, but we might be close to a point where we may be needing to export some of that heat across the Southern Ocean.
Okay.
And if you want to be even more speculative, you can look to the sea ice, is what happened this past winter, right, and lots of changes we're seeing in the Southern Ocean, but it's still early days to try to understand how this links onto what is very much a steady state picture. Yeah.
Andy, I forgot the detail. Is there any atmosphere circulation here? Or it's just all ocean? Oh, there is.
It's a couple planet models.
So what happens to the storm tracks when you have a reduced heat loss from the ocean at the location of the Kuroshio or the Gulf Stream? I should have asked earlier then.
Yeah, we did, so I'm not going to be able to answer that question on the spot here. We did look into that a little bit, and when you, if I go back too far. So, this heat loss is very sensitive to the shifting of those, where those storm tracks are.
Okay.
And so part of the transition you're seeing in the total heat budget is actually, there's a big component that's related to what happens in the western boundary current there. The takeaway, I think, from the analysis that Emily did on that is that it's the change between the atmosphere and the surface ocean temperatures that dominates the change in that heat flux, but shifting of those wind patterns is not insignificant.
Okay, thanks.
I'll ask a quick question
Yeah,
over
sure.
here. But wait, I thought the AMOC was going to collapse. Because I know that's on some people's minds. So I was wondering, have you or Emily looked into sort of the transient adjustments of these to try to get a sense of how the system goes from that initial collapse state into the more equilibrium state, which is what you expect here?
So I have promised Clark I would get to that part of my talk, and then we do have, so not in these simulations. So we don't have the transient state in these simulations, but we have looked at some other simulations that I mentioned before, the long run MIP ones, and I think I will get to those by the end of the talk. So but that is a really important point, that is all of these, so what I've shown here is not very helpful in terms of causality. It is looking at once this system re-equilibrates, this is what the overturning structure looks like and how it has changed, but it doesn't talk about phasing, and that I think we can get a little bit more of the transient simulation. Yeah, good. Okay, but that is a perfect transition, because that's all I want to talk about, the steady states, and now I want to talk a little bit about transients in the overturning circulation. So I'll go back to my very simple schematic here, and I'm going to do a very simple movie. So remember, my whole point is the overturning circulation exists to transport waters from sites of buoyancy gain. We just talked about that as being the Indo-Pacific, to buoyancy loss being the North Atlantic. Now I want you to imagine that you have some process where you transiently turn off one of these processes. So let's imagine we turn off North Atlantic deep water formation, right, as such. As long as the other processes are happening, so for instance, I'm still making intermediate water, for those who aren't familiar with the terminology, taking waters that upwell in the south and making them lighter, right, I will fill this density class, right? And similarly, if I'm no longer supplying this dense density layer with North Atlantic deep water, it will thin, right? And so I get this modification in the stratification. That's kind of the main thing. Okay, so let's go back to this picture, which I apologize, it's a little bit busy. Remember, this is a two-dimensional picture of the overturning circulation, depth, latitude, and I've just told you that the three-dimensional structure of the overturning is important, but I would argue that most of our sort of theoretical understanding of what governs the overturning comes from a very two-dimensional picture, right? One like this. And it sort of argues that there are two types of cells. Let's do the lower one first, where waters are largely sourced from the margins of Antarctica. They sink into the deep ocean, and they sink into the deep ocean along or within a density range where that density range does not come back up and touch the surface anywhere else, right? And if that's true, the only pathway for that water to come back up is actually across the stratification. And that is when you need to mix buoyancy into the interior and transform that water by mixing in the interior. Okay, and that's what we call a diabatic cell, formation of Antarctic bottom water, and then this diffusive upwelling. And you can contrast that with the upper cell, which is largely sourced from the North Atlantic deep water. It sinks, but it does so into a range of density classes where they don't have to change their density in the interior. They can very happily flow along this layer, move along these tilted density surfaces in the Southern Ocean, outcrop at the surface, and be exposed to heating, cooling, sea ice melt, or sea ice formation, and you can close this cell adiabatically, which is a little bit of a misnomer because the diabatic processes are just happening on the surface. This squiggly dashed line here is meant to schematically represent the the mid-Atlantic ridge. And so we think that there's some differences in mixing rates in the deep ocean at higher and deeper above, sort of that picture I showed you before. Okay, so let's just consider for the moment the upper cell, and now let's think about what might happen in a warming climate. And this was a question that Shantong Sun, who was a postdoc who worked with me, kind of came to me and asked this question. He said, well, we've been told in many papers that in a warming climate, you're going to have warming and freshening in the North Atlantic, and that's going to lead to a weakening of the AMOC, which would sort of reduce this sinking here. But in a warming climate, you should also have a strengthening of the surface wind stress in the Southern Ocean that is, as I mentioned to John earlier, partially responsible for drawing this water up towards the surface. And so if those two things are happening in a warmer climate, how does the system respond to what should be a weakening here and a strengthening here? Okay. And so this is the question we set out to ask on sort of decadal to centennial timescales. So we started by looking at a very simple system first. So what you're looking at here is a very idealized ocean model. This is latitude, this is longitude, and it explicitly has two basins. It's going to be important. So here's the Atlantic Basin, here's the Indo-Pacific, and this model essentially has an upper density layer and a lower density layer. And so it is allowed to move water from the upper layer to the lower layer, so that would be a downward transport, and it can move water from the lower layer to the upward layer, which is an upward transport. And then it can also transfer water across these different basins or into the Southern Ocean. And all we're going to do in this simulation is turn off this North Atlantic deep water formation, which is just parameterized by vertical velocity, vertical transport, and look at what happens to the transports at the southern edge of this basin. And this is so this is the forcing of the model. There is a wind stress in the Southern Ocean that's helping to bring waters up here in the Southern Ocean. And this is what you find, okay? So let's go through this carefully. On the x-axis here, this is time in years. The first 100 years are expanded here, and then this goes out to 3,000. And what the y-axis is showing is the change in volume transport, again, at the southern edge of that basin. And what you find is what you might expect. We've turned off North Atlantic deep water formation, so the flow into the Atlantic Basin in that surface layer weakens. Okay, it just slows down. But what we find in the Pacific Basin is that there's a perturbation of the opposite sign that, at least over the first 100 years, is almost the same magnitude and of the opposite sign. And if I look at what happens, what goes into the Southern Ocean, which is just the sum of the green and the blue curves, at least over the first 100 years, it's pretty weak. And I've just drawn the opposite of the Atlantic here to show that timescale over which there's this compensation. So over sort of decadal to centennial scales, there's a very strong compensation between the Atlantic and the Pacific Basin. And this kind of walks through why. Just do this a little bit quickly. Time is still on the x-axis here. This is showing the change in the transport into the Pacific divided by the change in the Atlantic. So a total compensation is 100%. And then over time, this decays. So what happens is when we abruptly turn off North Atlantic deep water, there's a really fast response of the density structure, right? The change in that layer between the Atlantic and the Pacific Basin that's propagated by Kelvin and Rossby waves. And this gives rise to a change in the stratification at the southern boundary of those gyres that gives you this compensation in the overturning circulation. And that happens over the first sort of 50 to 100 years. And then over time, you have this slow response where the Southern Ocean gets involved. You diffuse the change in stratification across the Southern Ocean. I won't talk about this in detail. If people are interested in this, that's kind of an interesting topic in itself. But over a period of 1,000 years, then the Southern Ocean becomes important. Right? Then you begin to see a change, and then you eventually reach a steady state. Okay, so this isn't a very idealized model. We also went and explored whether the same behavior happens in a more realistic model. So here you're looking at NCAR's CESM large ensemble, and this is just the sort of modern day run. So all of these panels are showing the stream function. This is the Southern Ocean, so this is depth, this is latitude. You have your upper cell here, you have your lower cell. And when I break out the overturning circulation into the Atlantic and the Indo-Pacific, again, you get this three-dimensional structure. So you have your AMOC, which is this strong clockwise circulation in the Atlantic, and you have in the Indo-Pacific here this counterclockwise cell, comes like this. And then what I'm going to show on the bottom now is looking at the mean of 40 ensemble members, which are forced by the RCP 8.5 emission scenario, so very strong warming. And what you find is, in the Atlantic, what you expect, you have this is the anomaly in the stream function, so a change. So the fact that this is a different color means that the AMOC is slowed down. But what you see in the Indo-Pacific is you see a positive anomaly, right, which is the same thing that we saw in the simple model, that this overturning circulation that you have here also weakens, okay, and you get this compensated overturning. And I just want to point out that when I've given this talk before a few times, this has been argued that, oh, I see what's happening here, because now you have this overturning anomaly that goes this way, you've generated deep water formation in the Pacific, or what people call the PMOC. This is not a PMOC. It's an adjustment that comes from a change in the stratification between those different basins. Okay? So that's interesting that you get this same response. I think the last thing I'll show is what is important, I think, for those circulation changes is how they tie to the tracers. Okay, so for this same simulation that we showed, if you have an abrupt reduction in North Atlantic deep water formation, what I'm showing schematically here is the sign of the anomaly in the circulation. So even though the AMOC is still in this sense, it weakens, so it has anomaly in this sense. And if I look at the sign of the anomaly in the Pacific, it has a clockwise circulation like this. And if I map now the sense of that circulation onto, in this case, just the temperature structure, right? So it's warmer near the surface and cooler with depth. That anomaly implies an anomalous heat transport out of the Atlantic. And in the Indo-Pacific, the sign of that anomaly acting on the vertical temperature gradient implies an anomalous heat transport into the Pacific. And what you get is actually a relatively small net heat transport into the Southern Ocean. Right? You have to wait 1,000 years to actually see an impact in the Southern Ocean. But you do see a strong subsurface warming in the Indo-Pacific. And if I just show you what that looks like from CCSM4, this is a slightly different simulation where we did 4 times CO2. We're going to do this, so abrupt atmospheric CO2. So we've shut down the AMOC, but this is looking at depth here and time on the x-axis of the warming in the Indo-Pacific. You can see over, again, a period of 100 to 150 years, you get an increase of a few degrees C subsurface, and you can actually diagnose where that's coming from. How much of that is because the atmosphere is warmed and you're just mixing heat down into the interior, versus you actually have this component of the stratification changing. And in fact, these isothermal deepening. And so the total change in heat content in the Indo-Pacific is here. So it increases by, whatever it is, 2 times 10 to the 24th joules. Some of that is due to the gyres, it's small content. Some of that is due to the surface heat uptake as they mixes in. But by far the strongest contribution comes from this right curve here, which is the transient change in the overturning circulation and the stratification. And so this is essentially an adiabatic component. It is not mixing heat into the interior, but it's what we call a heave. Right? It's the sinking of those warm density classes into the interior. And so I'd like to suggest that if you're interested in tracer changes due to climate perturbations on sort of centennial timescales, they're largely going to be due to these stratification changes and not necessarily mixing into the interior. And then work that's kind of still in progress here, you can do this with a lot of different tracers. So here, rather than heat, we're actually looking at the distribution of silicate in the ocean. I'm not a biogeochemist, so this has kind of been chosen simply because you see there are very different tracer concentrations in the Atlantic versus the Pacific. And in particular, in the Atlantic, there's very little vertical structure in the silicate concentration, and so you can have the circulation change, and if you actually look at your transport anomaly, it's really small. If you look at the same thing in the Pacific, where you have this very strong gradient in silicate concentration, that transport anomaly gives you a really strong anomalous transport of silicon into the Southern Ocean. And we're still sort of at the stages of trying to understand whether that's important with regard to other biogeochemical changes that happen in a warm climate. Okay, so that, I'll stop there in terms of the sort of decadal to centennial changes, and I'm going to spend just kind of like the last 5 minutes or 5 to 10 minutes talking about these longer timescale changes. But if there's any questions on this part, good point to pause for a minute. Yeah, John.
Implications for El Nino in the Pacific Basin then?
Oh yeah, so that is something that Emily Newsome was very interested in, and we kind of digged out a little bit. Okay, so mostly what I've showed you here is we've perturbed the North Atlantic and seen the change in the Indo-Pacific. So there's one question, which is, can you go the other way?
Yeah.
Right, if I perturb the Indo-Pacific, do I see the change in the Atlantic? And we expect you would. And the question is, does La Nina El Nino happen on timescales that are so fast that the decadal to centennial timescale you need to see these sort of wipes out that signal?
Oh, okay.
That is still very much an open question, and I suspect there's some part of that signal that probably does get exchanged between basins.
Thanks.
Yes, Sam?
You emphasized buoyancy early on, and then I feel like most of your story has been heat.
Yeah.
Is there a role for salinity?
There is a role for salinity, so yeah, so I think we were just having this, Taylor and I were just having this conversation earlier today, right? The water mass transformation that happens in the Indo-Pacific and the North Atlantic is largely a heat gain and heat loss story. So if you're actually thinking about water being transferred between different density classes, that's really important. The salinity plays a really important role in actually dictating to which density class North Atlantic deep water sinks. So it does feed back on the stratification, although I'd say less so on the volume transport, although I'd be happy to be corrected there. When you get to the Southern Ocean, the salinity plays a more important role, and in fact, what I'm going to show for the longer scale transients, salinity also plays a role. Okay, so let's get to the last part, and this one I think will be a little bit shorter. Okay, so yeah, well, I guess I'm going to address this somewhat head on. What is the role of temperature and salinity on just, now we're going to focus a little bit more on just the Atlantic, so Atlantic overturning circulation transients. And the tool we're going to use to look at this question is a relatively unique set of coupled climate models. So these are part of the long run MIP, so MIP stands for Model Intercomparison Project, simulations that have been compiled by Maria Rugenstein. We have 7 that we looked at that were all run for at least 1,000 years, and most of them were run for at least 2,000 years. And what we're going to look at is the 4 times CO2 experiment. So we're going to perturb atmospheric CO2 by a factor of 4. And what I'm showing here is time on the x-axis, and note it's on a logarithmic scale. So time is stretched here. So this is 100 years. This is 10,000 years. And on the y-axis is the strength of the AMOC normalized by its initial strength. Okay? And so in all of these simulations with that atmospheric CO2 perturbation, pretty much all of them experience some decline in the AMOC, which is at least by about 50%, some collapse altogether, but a really broad range of recovery timescales. Some start to recover within a couple hundred years, some require 1,000 years, and some of the models here may only just beginning to start their recovery after a couple thousand years. And the question is, why do these look so different? So as I've said, these are the long-run MIP models. This is just one of the plot. These are one model that recovers and one that does not. One can look at the color here as the maximum stream function of the AMOC, so it's strong, and then it's weak, and then it recovers. This one doesn't recover. But you can also look at the vertical structure. So this is actually the depth of that overturning stream function, and it shoals and then sort of deepens. So even though it recovers its magnitude, its vertical structure has changed as well. So there's a lot of subtleties in these simulations. But the way we're going to assess these models is, it's a little bit of a leap of faith here. So we are going to try again to link the density structure to the overturning. That's sort of the theme I've been going for here. And we're going to assume that we can use information about the north-south density difference, or the meridional density gradient, to get at the strength of the overturning circulation. And this sort of relies on the thermal wind relationship, which says that a north-south density gradient should be related to a vertically sheared flow. The challenging thing here is that if it's a north-south density gradient, it should relate to a vertically sheared zonal flow, not your meridional overturning. Now, there are a number of papers that have actually showed that this works pretty well, and I think the assumption here is that in steady state, that density gradient is balanced by a zonally sheared flow, and that as the upper layer moves eastward, it hits the coast and is carried into the Arctic, where ultimately it is transformed into denser density classes and feeds the westward flowing zonal flow coming out. Here's an example of what we tried to do. So you can take these different models, you can just calculate the difference in density between a northern region, say between 40 north and 60 north, and then a basin region here, just look at that density difference. And then you can just calculate, using the thermal wind relationship, the structure of the AMOC, knowing that the transport has to go to 0 at the top and the bottom. And so the black is the overturning circulation diagnosed in CESM1, this model here, and the purple is what the thermal wind relationship says. And so it seems to do fairly well. So here's a whole time series of that same model where we've calculated the overturning stream function and used thermal wind relationship. When you are going through a strong transient period, there's a bit of disagreement, but over most of the period, it works fairly well. And these are sort of the Pearson correlation coefficients for a few different periods here. And again, except during periods of transient change, it does pretty well. Now, the reason why this is useful is that we can start looking at what are the thermal and haline components to those density differences. Okay, so I'm just going to show a couple plots quickly here. These are the 7 different models on the x-axis. And what you're looking at on the y-axis is the contribution to the density difference that comes from the thermal component in red and the haline component in blue. And what we're looking at here is the initial weakening phase. What you find is that the change in the AMOC, which is in purple, where you have these strong shutdowns here, are largely driven by a change in the thermal component. So essentially, warming in the high latitude North Atlantic reduces that density difference and helps to shut down the AMOC, whereas these models that have a weaker AMOC change have a smaller thermal component. But I can contrast that with which is what we call the recovery phase, okay, where both the thermal and the haline components now are having a really strong role. In particular, what you're seeing here is now the red's actually flipped sign, which is a signature of actually low latitude warming, enhancing that density gradient. And while they both have a significant contribution here, what really sets the intermodal spread is the changes in the haline component. So I know there's a lot of bars on here, especially late in the talk. So the one maybe good takeaway message here is this second to last figure. Here are the 7 different models. Here's this sort of key period where we start to see a recovery between about 500 and 1,000 years. This is the change in the AMOC trend. So this is a strong recovery. These are models with weak recoveries. And what we find is that it correlates very strongly with the percentage of remaining Arctic sea ice. Okay, so those models that don't lose much sea ice, so 70% of this Arctic sea ice still remains, is much more likely to have a rapid recovery, whereas those models that lose almost all of their Arctic sea ice tend to have a very, very slow recovery. And so if we just look at 2 end members here, one which is a strong recovery, one which is a weak recovery, I'm just going to show the temperature evolution and the salinity evolution as my last plot. So time here is on the x-axis, again as a logarithmic scale. Y here is latitude, and this is showing the temperature increase in the upper 2,000 meters in the Atlantic basin. You can see warming comes in the high latitude North Atlantic first, and then you get strong warming at the low latitudes. But what's important is that the warming, you see, looks really similar between the strong and the weak recovery runs. Okay, there's not too much difference between these two. Whereas if we look at the salinity, the changes in the fresh water, this is the model where we didn't have much loss of Arctic sea ice. So you get a small freshwater perturbation after about a couple hundred years in the North Atlantic. You get a very strong salinity anomaly at low latitudes. That gets affected northward and essentially erodes that salinity anomaly. Whereas in those models where you melt most of the sea ice, you have this huge salinity anomaly at the surface, and it becomes very, very hard to have an AMOC recovery in that case. So the sort of takeaway message here is that the longer term, this was the question that goes back to Liz's point, right? In a warmer climate, why do we see these stronger AMOCs? In almost all of these runs, we do get a recovery of the AMOC. And in some cases, it's even stronger. But the timing of that recovery is very strongly dependent on the freshwater component, and probably is very dependent on how sea ice is represented in these models. Okay, I would probably want to stop there to leave time for questions, but I will leave up my key messages, and I thank you very much for your attention.
All right, grad students first. That's right.
So this is less of a question and maybe just connecting the early part of your talk
Yeah.
to the end here. You showed in your, like when you went from cold to warm, then warm to hot, you had that progressively higher placement where you were losing heat. And would you say that that's following like the edge of the sea ice extent in the winter season?
Yeah, so if I just go back to that quickly. I think, so I didn't talk about this specifically, but when we look at the change in the strength of the AMOC as a function of global mean temperature, the point where that AMOC strength saturates is largely when the sea ice goes away.
Yeah.
Right? We think that the fact that you're maintaining sea ice there helps you keep this very large atmospheric ocean temperature difference and allows you to have very strong heat loss. When that goes away, I think then you've sort of saturated the Atlantic's ability to export heat, and that's when you get that transfer into the south.
Okay. And are there feedbacks in some of the models that are run very long that stop any ice from forming in the Arctic? Like you have circulation changes that keep warm water that stops any ice from forming, and that's what's stopping the
Yeah.
circulation?
Well, so I think that's a good question. I think that gets to a question that I was chatting with Clark with earlier, right? Is there a steady, stable state in which the AMOC is turned off, which I think would correspond to a state where you're not going to grow the sea ice back at all? Well, I should be a little bit careful. I have not looked at time series of what the sea ice looks like, and I must be careful because I don't know what the sea ice state looks like during the recovered phase.
Okay.
But my sense is that as you recover the AMOC, you start to get you certainly have an overturning that looks a lot in terms of its strength and structure, like today. And presumably you need to have strong heat loss to support that in the sea ice mechanism.
Okay.
Yeah.
And then the last part of that thought is there a chicken and the egg question where if you have AMOC starting back up, that'll help take those low salinity waters away from the Arctic, and so they aren't staying there. And so,
Yeah, I definitely think that's true, right? And it is two things, right? It is, so I did go back and look, and we have done some of the water mass transformation calculations in the recovered state. The overturning is still driven by heat loss. It's still a thermal component, but I do think that the advection of the large salinity anomalies at the low latitude are really important for eroding the fresh water signal to the Arctic sea ice. Yep.
Thanks.
Sure.
Yeah, hey Eddie, great talk. And I'm kind of building on what Evan's question was. So after sea ice, and I'm surprised to see that it matches up so well with sea ice. It's very interesting. I'm curious about what about ice sheets, because they also have a large influx of fresh water going into the ocean. And I thought that might have a larger signal given all those hosing experiments paper I have seen. Do you think that those play an important factor in this results or not?
It is a good question. We have definitely not looked at the freshwater contribution coming explicitly from the ice sheets, so I don't have a good sense for what the magnitude that is for the freshwater perturbation there. Yeah, I mean, other than showing that the freshwater anomaly and or I should say the recovery rate is very strongly tied to the sea ice extent, there may be, it may be that there are similar types of behavior in terms of how much fresh water is given up from the ice sheets in those models, but I don't know what they look like. One of the things to take away, right, is that the sea ice and ice sheet components of these coupled climate models are probably the parts that will have the most variance across different models, just because they're models that we don't understand the equations as well as we do for the atmosphere and the ocean. And so the sensitivity to the cryospheric part, I think, is a little bit, is worth considering how we look at diagnostics going forward for change.
Yeah.
I got a kind of broad question. So this is super cool. It's made me wonder, most of this is done with 1 to 3 degree ocean models. And we know that there's, I'm thinking that's probably CM2MC in there. And there's a lot of huge biases, even with 1 degree ocean models, with the representation of currents. They're much more diffusive, not as many eddies. They don't have the right placement. They're not going as far northward. But maybe all of that doesn't matter. And I'm curious what your thought about is for what features of transient changes of the equilibrium climate do these kind of things not matter, getting the specific high resolution meanders and currents right, and what does it matter for?
Yeah, okay, so you partially stole my answer, right? Which depends on whether you want to put the optimist or pessimist hat on, right? So the optimist hat is these models want to close budgets, right? They want to close a heat budget. And so if you think about especially low latitude ocean heat uptake, that should be really very strongly dependent on small scale processes. I wouldn't expect that, especially when you consider that most of that happens right at the equator due to Ekman divergence, right? And so it is going to export that heat to high latitudes, and so your overturning will have to adjust to accommodate that. And so in a coarse model, the ocean may do a pretty good job of doing that. We do know that when you get into the high latitudes, so I've thought a lot about what happens in the Southern Ocean, how you export heat, say, across the ACC, into the Antarctic margins, how you give it up either to the atmosphere or the ice shelves. That depends a lot on small-scale processes. And so I am a little bit more pessimistic about how the ocean consumes that heat, right? And how well it's representing those processes and how that might lead to bottlenecks that could lead to changes in the stratification in the real ocean that these coarse models can't represent, much stronger fronts, et cetera. I would have said I was a little bit more optimistic about the Arctic, but so the conversation we were having earlier today about the role of exchange between boundary currents in the interior, if that plays an important role, then that's not being captured by these models. So, if I had to summarize a somewhat rambly answer to your question, I think probably the amount of heat transport the models do is probably right, but the stratification it has to achieve to carry out that heat transport may look quite different. And so the feedback on that on different biodiagonal tracers or where the heat and salinity is redistributed through the ocean could look different. Yeah.
Two questions. If we have time. Quick. Just out of your curiosity, so what does the global mean temperature profile look like as we go along here, like in the CO2? So you quadruple it, and then...
So I don't know off the top of my head, but it goes up pretty substantially.
It goes up and then it stays up.
Yes.
And so that's why we see that sea ice.
So yeah, this is why you would be.
It doesn't really recover, right?
Yeah, and in fact, I didn't talk about this. So yes, this is part of the reason why you see the sea ice loss. It's also the reason why you see this very slow accumulation of heat in the low latitudes, which in part plays a role in reestablishing this north-south density gradient, right? So you start heating in the high latitudes, thermally you're eroding that density gradient, but over time you accumulate this heat in the low latitude. This is in the Atlantic, but remember some of this might actually come due to interbasin exchange between the Pacific and the Atlantic. You do reestablish this north-south density gradient even in the thermal field, which at the low latitudes is dominating the density structure. It's the heat.
And then just quickly, I wanted to ask you, how, a lot of the focus on Amok Shadam is on the hosing experiments,
Yes.
and then there's even Liz introduced me to NAHOSMIP, the North Atlantic hosing.
Yep, I'm aware of it. Yep.
Yeah, right. How does that relate? Because the thought there is the AMOG is so sensitive to the large scale freshwater input from the ice sheets, follow up to address the question.
Yeah, so I think, those, I think it depends a little bit on the lens of which you're viewing it. So you can take those experiments and you can still do a water mass transformation analysis. And I think you can learn important things about how the system recovers from a perturbed state like that and what the relative role of thermal and haline component are. I think a freshwater hosing experiment may give you a very different recovery trajectory in terms of those different processes than just increasing your atmospheric CO2. Yeah, I think, I mean, there's lots of interesting things that it's still really very much work in progress, so it's not anything that we've finished up, but even changing precipitation patterns even in the Indo-Pacific, although it doesn't dominate the buoyancy budget, can have some role in setting the density structure. Things that you would capture in a perturbed atmospheric CO2 that we wouldn't just with those. Question?
Oh yeah, so my question is, I'm not an oceanographer, so it's a little bit different, but it's really interesting that you say that the circulation changes in line with when the sea ice disappears, essentially.
Yes.
So from a stratosphere perspective, the strengthening or weakening of the polar vortex in a future climate is very dependent on the time when the sea ice disappears. So some kind of models say they'll strengthen,
Right.
but it's all dependent on whether or not sea ice disappears. So I'm wondering, that implies large-scale atmospheric circulation changes and on a big scale. So how much of that large-scale atmospheric circulation change is in this difference between the AMOC circulation and sea ice disappears?
It's hard. We did not look at very many of the atmospheric diagnostics, and it would be a nice thing to go away and look at. I mean, I think even just one of the things we have talked about and sort of scratched at a little bit is just the partitioning of heat transport between the atmosphere and the ocean coming up. The Arctic, and thinking about that, but yeah, I don't really know what that answer is. Yeah. Thanks for the question. Yes.
So I know you said that you didn't actually look at like the sea ice extent, but I'm just curious, like in the left-hand plots, it just seems like the ocean is a lot saltier, and in the right-hand plots, it's a lot fresher. And of course, like salt can't just disappear. So are we assuming that just the left-hand plot, there's just the ice is reforming, and on the right-hand plot, there is no ice forming?
Well, so there's two different things going on, right? So the freshwater anomaly that's happening between, say, 50 and 60 north is probably largely dominated by changes in sea ice, like sea ice melt. But there is something happening as well in the low latitude, so that's largely a signature of just E minus P, so much stronger
right,
evaporation.
this is 30 north to 60 north, not 30 south to 60
Yeah, 30 south to 60 north.
Oh, this is 30 south to 60
Yeah, so this brown area here is probably due to much stronger evaporation, and so there are additional things. Like again, the strongest signature was the correlation between the recovery rate and the sea ice, but there are also differences in the hydrological cycle.
But so then why are we not seeing that strong evaporation signal in the other model?
Don't know.
Okay.
Probably differences in the changes in the atmospheric circulation, changes in moisture transport. There could be loads of different reasons, and I think that's so. This is one. So Dave, who led this paper, will be finishing up in about a year, but he's very interested in sort of pursuing some of the hydrological components, like the sort of atmosphere, land, surface interactions and what their impact here is, and not just the ocean component. But I think that's an area that we just don't understand very well.
Along the same lines, I'd love to know, I always ask everybody this who's an oceanographer, what's the role of cold air outbreaks in the cold season over the Labrador Sea? And how big a component is it for some of these differences? Because they can be enormous. They do everything. They make the water more saline and they cool it. And they happen all the time, from November to March.
Liz, I think, and her group are probably going to have a good answer for that. It is interesting. I think I have very much talked about the Arctic as this bulk ocean region where they're sinking, and it's a much more complex place where different basins are playing different roles. The sense is that most of the water mass transformation is not necessarily happening in the Labrador, but a little bit further north.
Oh, okay.
But still to be determined.
Okay. I'm not allowing any more questions.
Sorry.
That's all right, it's great. I very much appreciate it. Thank you all, and let's give Andy another round of applause.